determine the health of all 20 of their transformers. So today we'll do a client introduction, and I'll talk about the transformers and how they work, as well as dissolved gas analysis and why it's so important. And then we'll continue with common methods used in the industry today, as well as our analysis and the conclusions that we came to, some of the limitations we faced during this process, and we'll end with a question and answer session. So to start off, our client is Weatherford Electric, and they are in the business of distributing electricity to customers. Our client is Mr. Doug Evans, and he is an electrical engineer at Weatherford. This is a photo of us at the substation. Those of you who don't know, Weatherford is located outside of Fort Worth, so it's about an hour and a half from our current location. And he is basically explaining to our very confused faces about how transformers work and why they do the dissolved gas analysis. Weatherford serves an area of 52 square miles, and they have over 13,000 customers. And they have an annual energy purchase of 357 million kilowatts. Weatherford does not produce their own electricity. They have to purchase it from an outside source. And they distribute electricity through 139 miles of underground and 174 miles of overhead lines. And they have 20 transformers, and it's all 20 transformers that we looked at to determine their health. So to start off the transformer, so a substation is part of a generation, transmission, and distribution electrical system, and the main purpose of transformer is to take voltage from either high to low or low to high. So as I said, Weatherford needs to purchase their electricity, and so when it comes into their substation, it's at a very high voltage, and so it needs to be brought down to a lower voltage so that it can be distributed to their individual customers that live in residences and small businesses. Transformers have several different components, and these components vary depending on the type of transformer. The three main types: oil natural, air natural, oil natural air force, and oil force air force. The 20 transformers at Weatherford are all oil natural air force, which means that the oil and the air circulate naturally, but there's also fans that perpetuate the circulation of the air. So oil natural air force transformers are composed of windings or coils, oil, paper insulation, heat exchangers, pumps, and flow gauges. And how a transformer works is that the coils produce heat and the oil absorbs its heat, causing it to become less dense. So it rises to the top of the transformer and overflows into the radiator and into the radiator tubes. When the oil comes in contact with the air that's at the top of the transformer, the heat is then transferred to the air, causing the hot air to rise and replaced by the cooler air, which creates the air circulation, which, as I mentioned before, is also perpetuated by the fans. Now that the heat is no longer in the oil, it becomes denser and sinks back down to the bottom of the transformer, and this process continues, keeping the system cool. This is a photo of the two transformers located at the substation that we visited. The number of transformers at a substation depends on the size of the client as well as the amount of electricity that needs to be distributed to a specific area. So substations can have as many as 6 transformers, some as few as 1. It just really depends. So dissolved gas analysis, or we'll refer to it as a DGA from here now on, is just one type of test that can be conducted on a transformer, and you can kind of think of a transformer as a human body and the oils of blood. So the DGA is kind of like a blood test for a transformer. Over time, the oil breaks down and it releases various types of gases, and from these different gas combinations, we can determine the types of faults that occur. And there are various faults: there's sparking, arcing, overheating, etc. And these can create severe issues within a transformer and prevent it from being able to function at its highest capacity. And these problems can even cause a transformer to blow up in some extreme cases. And this is really important because transformers cost millions of dollars, and it also takes about a year for a transformer to be replaced. So if a transformer was to blow up, it's not a cheap fix and it's not a quick fix. Also, just taking a look at that one particular substation, if one of their transformers were to blow up, then they're down half their ability to distribute the electricity, and that can be a serious problem for the company. Another reason why this test is so important is that the gases can break down the paper insulation, and this can seriously impact the way the transformer breaks down, and once the paper is gone, it's gone for good. There's no replacing it. So this is a major issue, and it's one of the reasons why we take a look at the DGA to keep track of the faults that are occurring and to make sure that the transformer is staying as healthy as possible for as long as possible. This is just a picture of the gas sample valve that's located at the very bottom of the transformer, and it's where the test is done, and the sample is taken for the dissolved gas analysis to be conducted. I'll now pass it on to Shannon, and she'll talk about methods used in today's industry.
So when we were creating the plan for our project and thinking about how we're going to go about tackling this huge problem, we thought first we'd start with what is already happening within the industry. So we do our own analysis based on these methods first, and then after we do this, we'll go through and say, hey, we think that we can make this easier and better for the client. So I'm going to start by telling you what we did based on the analysis that currently happen in the industry. So the first one I'm going to talk about is the most basic one. It's the guidelines for combustible gas. And we did this using Microsoft Excel, which we'll see in just a minute. And then we will go through and do Duval's triangle, which you can do it on a computer program. We did it by hand. So I'm going to explain both of those and the advantages and disadvantages to each and what we found from them. So the data that we were provided with was about 10 years of data per transformer with 20 transformers. So this gave us about 200 counts of data from different tests that have been done on the oil in these transformers. Additionally, for each test, there are 10 different gases that we were given the amount of at that particular time that's in the transformer. We were also given the age of the transformers except for numbers 17 and 18. So we were missing those pieces of data for those two transformers. Okay, so this is the reference table for our first analysis. So what you're seeing here is for each gas, there's a normal and an abnormal range. And we want the gas to be in the normal range. If it's in the abnormal range, that means that danger, warning, watch this transformer because it could explode. That's a little extreme. But if you see the interpretation on the far right-hand side, that does tell us the problem that is most probably occurring within the transformer at that time. So for example, the first gas up there on the top is hydrogen. So in the normal range, we want hydrogen to be under 150 ppms. If it's abnormal, that means it's over 1,000 ppms. And so if it's abnormal, then that means that arcing corona is happening within that transformer, or most probably happening. So as you can see, there's a normal range and an abnormal range, but there's nothing really in the middle. So the way that we interpreted that range is that it's just kind of neither. It's neither good nor bad. It's a kind of a warning. It's like, keep watching it, but you don't have to go to any extreme measures yet because there's nothing really bad happening at this time, but it could potentially in the future if it keeps increasing. So on the next slide, we see the total combustible gases. So instead of breaking down each gas by the normal and abnormal ranges only, we can also do it by interpreting the total combustible gases, which is an analysis of the total of all 10 gases. And there's 4 ranges here. So there's normal, decomposition, all the way down to bad decomposition, where you want to be testing that transformer weekly to make sure that nothing really bad is happening. And then our analysis using this. So this is an example of transformer number 4 specifically. But we did conduct the same analysis for all 20 of the transformers. So I'm going to explain this a little bit. So if you look at the colored part, this is basically a color coding of what I just showed you. So this is pretty easy. We did it in Excel. The green cells mean that those gases are in the normal range at that time. The red cells mean that the gases are in the abnormal range at that time. And the white is that middle kind of nothing region. And then on the right-hand side, you see the results depending on the analysis of these gases. So for example, for transformer 4, on December 13th, 2002, go all the way to the right, that means that arcing corona is happening at that time. So it changes over time because the amount of gases present can increase or decrease. So sometimes you may see something present and sometimes you might not. And that's okay, that happens. But as you can see, as the transformer is getting older, there are more of these problems present that could be occurring within the transformer. So the conclusions from this analysis, so transformer 4 is probably experiencing at these points in time a combination of arcing corona, sparking, local overheating, severe overheating, and arcing. Some advantages and disadvantages that we saw to using this method. So it's very comprehensive. It uses every single gas and it gave us a range of possibilities that could be occurring. So it was good in that it gave us the most information out of any analysis that we conducted. But it's not able to specify what is actually occurring. So these are just predictions, but it's not able to pinpoint one in particular that's most likely. Based on the color coding that we did as well, it's actually very easy to identify the health of the transformer just by looking at it. So if there's a lot of red in this transformer like we just saw, that probably means it's getting in pretty bad condition. Additionally, this was very, very time consuming and tedious because we did have to do this analysis for every single gas at every single point in time. So time-wise, it's not the most efficient method to be using. So the next analysis that we conducted that already exists is using Duval's triangle. And this is a little bit different. It only uses the gases methane, ethylene, and acetylene. And the steps that we go through, I'll show you the triangle in just a second, but it's basically a triangle and each gas has a side of the triangle. And the first step is to determine the amount of increase in each of the gases. And then you plot those points on the triangle by drawing a line straight through. And the point at which all three lines intersect is the pinpointed problem that is most likely to occur. So I'm going to show you an example. So we're going to take transformer number 14, and the increase in methane at this particular point in time was about 17%. So the methane line is right there on the left side, so you find 17% on the left scale and draw the line all the way across. And then if we do that for ethylene, which the increase is about 58.5%, you can see that line down there on the ethylene side. And then acetylene is about 24%. So you draw that third line, which pinpoints the problem in the DT range, which that means there's a mix of thermal and electrical faults. Yes, thermal and electrical faults. So each of these sections in the triangle represents a different problem that is most likely occurring within the transformer at that time. So these were the results that we were able to conduct, and I'm not going to go through all of these, but this basically just shows us for each time that we did that, what we concluded. From this analysis was even more tedious than the first one because we had to go through and calculate the increase, draw the lines by hand for every single transformer. The other downside was that we could only do this analysis when all three of the gases increased. So we couldn't do this analysis when there was a decrease in one of the gases, which really limited our information. It wasn't as comprehensive as the previous one. It only gave one problem, but the upside to that was that it pinpointed a most likely solution, whereas the Excel analysis didn't. So now I'm going to pass it on to Mariana, who's going to take our analysis and turn it into a solution that we came up with, two solutions that we came up with to make this process easier.
So as we mentioned before, one of our goals was to make these a tool for the client to be able to use it anytime they get a new test result. So the first thing we created was a flowchart. So it's mostly based off the Duval triangle, and it's like an if-then analysis. So as we go through, first it goes through the levels of methane, and for example on this side, if it's on the range between 0 and 87% increase, then we can move on to ethylene, and then we will go like, for example, to the first range, 0 to 19.9, and then we'll go to acetylene, and then it'll determine based on that particular read in what problem we are. So the good thing is that it's a more visual way to do it than the triangle, and it involves less calculations, and you can just pretty much follow a path. So as it goes on, we can go on and on like through the whole thing, and it just gives a very good result without having to, go ahead and draw out every single triangle. So we really like the flowchart as a tool to kind of like visualize and how to get to the problem, and it's a very good if-then analysis. But we took this analysis and we decided to simplify it even further. How can we make like a calculator for the client to be able to just input the results of the DGA analysis, and this is the problem that's occurring. So that's what we did. And we're gonna go ahead to the next slide. So this DGA diagnostics calculator, that's how we're calling it, we develop it so it can give you the one likely condition that's occurring within the transformer. And it's based off of the flow chart, which is based off of Duval triangle. So all of these data points and everything, they're used in practice. We're not just coming up with them from nowhere. And it will also allow that for the user to input the results directly from the DGA analysis. So for example, all the ppms directly. And it will calculate the percentages and everything of the accumulated and the increased gas. So it'll be a very easy tool that can directly use the results. And I'm going to show you a little bit of how that works. So these are results tab. The whole tool is going to be, it has instructions tab, results, and the background The background tab is where like all the logic statements are, so that is locked and no one can touch it. But here the user can input the results on the top left-hand side if they already have the percentages that they want to use. But if not, they can go ahead and put it on this table. And they can put in the previous VGA results and also the current VGA results. And you'll calculate on the bottom yellow area the percentages that then they can use to like input at the top. And then something important to note is that wherever the diagnostics label is, that's the problem that is happening. So it'll like automatically move depending on the labels to indicate what is the problem. And another important thing to consider is that for this test, we did a lot of reading and searching and everything. So for example, we found out that using both the accumulated gas and the increased gas value, the percentages and the results, if they both match, it's extremely likely that that problem is happening. So you can imagine if, for example, we have the arcing corona, which means that there's some electrical discharge and some thermal discharge that can probably cause like a fire inside within the transformer. If they both indicate that, then we know, like we have to shut that down or see if we can like redirect the electricity to the current to some other transformers. So this can be done in honestly like less than a minute. And this is an example for the accumulated one. So the user inputs the results on the previous DGA and the current DGA. The percentages are given, so then you can go ahead and put them on the top, and we get that the diagnostic is working. So then that can be written down at the top right table. And then on the next one, we can use the increased values now, put it at the top, and we now get sparking. So we know that they don't match up. It's not arcing, both of them. So in a way, that's kind of good. It's probably not necessarily like a red flag, but because arcing and sparking are very similar in nature within the transformer, that means that, you probably should check it out, see if there's actually like any other faults in it. And then, so after looking at both of these, we like the idea of giving a tool to the client to be able to use anytime they want it. And we realized that both, like they have obviously advantages, but also some disadvantages. So one of the disadvantages would be that the flowchart takes into account decimal value. The tool only takes whole numbers. And they both work when there is an increased gas, not necessarily when the methane, ethylene, and acetylene decrease. And diagnostic, as we know, it's not necessarily conclusive. Just because we get one result doesn't mean it's actually happened at the moment, but it's very likely that it's happening. And these two are recommended methods to approach, because even though they can go ahead and use a Duval triangle or any other method that they want, this is the least time consuming. Because in practice, you're probably not going to sit down and do this everyday analysis like if you had a huge Excel file. So having these simple tools can be really helpful to actually identify what's going on. And so finally, about some limitations. Some of our tests are missing information. As we mentioned before, there were some values missing. And we do not have the records if any transformers actually failed in the past. So for example, maybe it was predicted that there was sparking, but we never really knew if it actually happened or not, based on the data we received from our client. And that affected a little bit on our recommendation that our client made. He suggested that we do Bayesian statistic analysis, which seemed really interesting, and we actually attempted. But we realized that if we didn't have that evidence that we needed of what actually happened, or are we just hypothesizing that's happening, we couldn't really come with a conclusive result. So we took the calculator tool instead. And finally, we came up with our conclusion of which transformers are working in good condition, spare or bad. So at the top are all the transformers that are in good condition, which is great. There's most of them. For condition, there's only 2 transformers. And for bad condition, there's 5 transformers that are in that range. So that's definitely a red flag that they should take note. And then we further analyzed what was happening with those transformers, and we realized that with 14, 15, and 16, they were made in 1995, so that's only 20 years old. These transformers can last up to 40 years at least, and that's like prime condition. So there's something wrong if it's only 20 years and they're already in bad condition. And we also realized that all 3 transformers were manufactured by GE. And all the other ones were manufactured by different companies. So that's something that the client can take into account and realize, maybe we shouldn't buy any more from General Electric, or maybe we should go ahead and ask them, what's happening with them. And now we're gonna open the floor for any questions.
So your flow chart and your data, your calculation stuff, is that based off of the triangle, or is that based off of both?
Oh, the triangle. The
Okay.
triangle is where we got all the values from,
Gotcha.
but yeah, it was easier to map if you just saw a flowchart or if then.
Dr. Bosch, you have power engineering background?
Oh, that's one of them. Did you end up having to do any kind of forecasting or anticipation of failure, or, you had, 10 years or 20 years worth of data?
Yeah, we had 20 years of data, but our main issue was that we didn't really know exactly which one, like if it was actually happening or not. So we did some calculations with forecasting, and we came up with the same results that we got with the calculator. So that's why we simplified it down to that. We could see, like with the Excel analysis, a continuous pattern of problems start occurring. So like if you saw Transformer 4, there was a lot of red and it was continuing throughout the year. So something that we noticed was that our clients weren't taking the recommendations based off those tables. Like if it was in a specific range, they were told to test between like 3 to 6 months, and they weren't testing for another year, which was a serious problem. We don't know why they weren't testing for a year. Also, as we mentioned, we were missing a lot of data for a number of the transformers, which really impacted us being able to do any forecasting.
Maybe the market will cool after.
We figured out that.
Questions from the judges, panelists here?
Yeah, I have a question. I was curious, how much of a challenge was it? You obviously, all of you got pretty in-depth on your knowledge of electrical engineering, and so for this project, and I was wondering how much of a challenge was grasping the subject matter versus just doing the analysis on the data?
Well, Dr. Singh was really helpful in giving us, like that human body analogy that I gave you, that was really helpful in just being able, for us to be able to conceptualize it. And also Doug was really helpful in explaining the process while we were at their substation, and he was always available to answer any questions that we had. Dr. Singh also provided us with a number of sources, so we had, our first step was basically to read through all of those documents, understand how transformers work, what a dissolved gas analysis is, why it's being done, all of that stuff, and that did take some time. But I think we were able to get a pretty solid grasp on it.
Absolutely. I noted all three of you had a really good grasp of the subject matter, and that's good considering it was a complicated topic.
And I think it's kind of like, it's a little bit of the beauty of management science, how being able to, immerse yourself in that problem and understand exactly what's going on. Because if you go in consulting, you might do it for one industry and then go to another, so you don't really know which one you're gonna get. So I think like the classes in general prepared us for that, but then the information that Dr. Singh gave to us, that like made it perfect.
That's one of the things that I always have taken pride in, coming from the OR background, is the one thing that you learn and that you're going to be practicing is that you never know what your next problem is going to be. So be prepared that you may know nothing about it, but you have been trained to learn quickly about the problem. And so when this team, I approached this team knowing fully well that, as I mentioned, that they couldn't tell a substation from a subway station. But I said, after all, these are EMIS OR students, and this will be a good test. Let's see how quickly they can immerse into it and pick up. And I'm really impressed the way, while you were all going through all the gas analysis, and I deal with a lot of electrical power engineers, and I said, they could easily take a class from this team. As they talked about, it is a serious problem. What is happening is, as America's population is aging, so are the transformers. They are aging. They are in their 40, 50th years, 60th years, and they were not designed to last for more than 40 years. So utilities are trying to get as much out of this, the ounce of juice electricity out of this, because they are very expensive. They are resorting to buying transformers from Korea and other countries, which are cheaper, but they don't have the lifespan that other transformers had. So what is happening is there are third-party large companies, they take oil samples, but they treat the whole thing like a black box. They won't give you the data. They will just tell you, just like doctors, whether you are going to live or not and for how long you're going to live. What this attempt is that let's take the samples and create a kit that you can diagnose and you can come up with your own estimated approach that, yeah, we still got 3-4 years left in this transformer. Or we can continue operating certain ways to prolong the life of this transformer. So this tool that you have come up with is going to be very handy. We are going to be offering it to, suggesting it to other utilities that here is a handy, simple tool. Because the Duval's triangle, when presented to smaller utilities, they think that it is rocket science, and they said, we don't want to deal with it. But I think you have simplified something that they can look at and get a handle on this. Paul?
Yeah, I think this is quite frightening. I'm afraid to drive past a transformer. Now, again, obviously, you've really delved into the analysis and the difference and I don't know how you did this in such a short time. But with the tool that you're creating, over the years, they have just bypassed the need to upgrade or even to test their transformers. How do you see this tool influencing them to make some major decisions?
I think because how currently they do like 10 different tests, that some of them are the oil gas analysis, some of them are very different, and they're usually more costly, the other tests. But the dissolved gas analysis is very cheap. And as you saw with the picture of the valve, it's really easy to get to. So I think if they have a tool that you can tell them, just identify these 3 gases, that's all we need right now, and tell us what the values are. I think that's going to make it more like an easy test and so much more approachable than having to like shut down the whole thing or do something drastic and do multiple tests.
Okay, what I'm hearing is that if I adhere to the tool and the results, I may just have to change a valve and not a transformer?
No, you can just check it through the valve that we showed, but I mean, if the transformer is having issues, you still have to make sure something, like if something is wrong. But it could make the testing a lot more approachable. So if we say test in 3 months, they might actually do it rather than not.
So you can de-energize and do a quick maintenance as opposed to going with the recommended maintenance schedule by the manufacturers like GE that you do it every 3 years or 4 years. Now you may have to do it every 6 months. Then you have to look at and see how expensive it is to do the open heart surgery, so to speak, on the transformers. They can become very expensive. So it becomes a utilities decision. And with this tool, you're just giving them a way to look at it as opposed to sending it to SD Myers in California and waiting for them. And they would never give you the data. They will just tell them, yeah, it's okay, just keep operating. So, very good. I think good job. Okay. So now from power engineers, we are going to turn this over.